Yeah, thank you so much for the invitation. It's a great pleasure and honor for me to give a talk here, so I hope you can hear me clearly.
Yes. You're audible, perfectly audible.
Thank you so much. So let me start by sharing my screen. Okay, so I hope you see the slides. Again, I mean, let me thank you so much for the invitation. It's really a great pleasure for me to be here. Unfortunately, I cannot be here in person, but I hope also, I mean, virtual talk might be interesting. So I think we live in very exciting times. We see artificial intelligence, I mean, impacting our lives in various manners, not only in society, but also in science. But on the other hand, we are also aware that there are still many challenges to be overcome, in particular concerning reliability of artificial intelligence and then sustainability of AI. In that sense, I mean energy efficiency. And so here in this talk, I would like to take you on a short tour through these two areas, approaching them from a mathematical perspective and showing you, in that sense, the power of mathematics to take those problems. And interestingly enough, it will lead us also to reconsider the current way we do computing. So let me start from a high-level viewpoint. As said, we are, I think, in very interesting times. We are at the beginning of the fourth industrial revolution through artificial intelligence. What we see right now, I think, is a glimpse of what will happen during the next years. AI is transforming how we even create knowledge, how we do innovation, how we make decisions. And so this certainly then requires in particular that we take a close look at how reliable, how trustworthy these methods are. And I think let's say the disruptive change, what we are expecting, you see in the other three industrial revolutions which already happened. So the first, second, and third. And each time, basically, I mean, there was a disruptive change of the entire society. And I think with AI, we're looking forward to that as well. And we see some examples already now. And here are some of those where we see that AI is already becoming infrastructure for our countries. Think of autonomous driving, think of mobile communication. Then, I mean, one application where AI is maybe one of the most present one is the healthcare system, but also financial systems. But then, I mean, also science is changing in a very, let's say, comprehensive manner. So right now we are talking even of autonomous discovery. In mathematics, we have lean, which can already prove theorems and which can, to a certain extent, also verify theorems. And then, I mean, I think I also don't need to tell anyone that on the educational side, AI also has a significant impact. So in that sense, I mean, AI is becoming infrastructure of our society, but also of science. And so in that sense, I mean, one can certainly ask, and I think it's absolutely key to ask, we would like to develop AI so that it serves humanity. So this is this label AI for good, also from the United Nations. And so this certainly requires us to ask questions like, can we trust AI? Can we explain it? Can we, in that sense, make it transparent? Also can be govern it, and also can we sustain it, so in the sense of energy efficiency, that it doesn't hurt the environment. And here in this talk, I would like to focus on two of those topics. One is reliability, and the other is sustainability. But as we see, I mean, there are many questions, let's say, around, which also aims for ensuring AI for good in that respect. So we are now heading towards reliability and sustainability, and I would like to start with the grand challenge of reliability. So,
এই ছোট তীরটা
Why
টাচ
is this a
করবে
challenge? We all
টাচ
know
করে
that
দেখবে
we
একটা
still
ম্যানেজ
have
রেকর্ডিং
problems
বলে
with,
অপশন
let's say,
ম্যানেজ
safety.
রেকর্ডিং এ গিয়ে
So
অলরেডি যেটা স্টার্ট
AI in
মানে
particular
যেটা
language
রেকর্ডিং
models
চলছে
can
ওটা
hallucinate.
একটা স্টপ রেকর্ডিং বলে অপশন
Mistakes
সেভ
can
ওটাকে স্টপ করে
happen.
আবার
Also,
যখন স্টার্ট হবে স্টার্ট করে
robotics or self-driving cars can make mistakes. There are accidents, and so since AI is becoming infrastructure, this then immediately leads to a failure of critical infrastructure. So in that sense, it's absolutely serious if something happens. Also, there are problems with security. One can hack into those systems, and then last but not least, I might say problems with responsibility. So these methods are typically black box decisions. We don't really know how decisions are taken. Decisions can be bugs. So in that sense, I think it's fair to say that one major problem worldwide is the lack of reliability of AI technology. And as we, I think, all believe, what we require is a deeper understanding, and that can be only ensured if we take a mathematical perspective. So why a mathematical perspective? So AI, I mean, from my viewpoint, is a mathematical discipline. I mean, all terms what is dealt with also in computer science can be formalized in mathematical language models, learning, representation, power generalization, explainability. All of those have analogs in the mathematical world. So understanding AI in depth requires intrinsically mathematics and just, I mean, to be on the same side. Yeah, so a deep neural network. This is just the definition. It's a highly complicated, let's say, complex combination of affine linear terms and linear activation functions. And so in that sense, everything is rooted in mathematics. I think that's, I mean, very exciting. So we have our tools to attack those problems. So what are people looking at to ensure reliability? One is this area of expressivity, which is maybe the furthest developed. It's the oldest, analyzing which network architecture to choose. So this is typically approximation theory. The downside is a bit that this area is typically delinked from the training process. So it's more, these are more existence results. Learning, analyzing the training algorithm, people take stochastic gradient descent. It's not clear why it converges, because the problem is highly non-convex. So also there is, I mean, let's say, a lot of room for research and demand for research, and then the generalization, which is in a certain sense the most important of those directions, deriving error bounds to ensure that the out-of-sample error is controlled. So this is maybe, I mean, what in particular, if you think of critical infrastructure, is of essence. And then there's this area of explainability, which is a little bit different, because here we already have the neural network, we have the AI system. Can we understand how decisions are reached? Why is this important? Well, it ensures trustworthiness. We can understand also if something wrong happened, maybe during the training process, if mistakes were made. And I mean, in many countries worldwide, also in the EU, where I'm coming from, it is also now required because it complies with legal regulations. So in the EU, every AI technology has to come with an explainability approach. So let me now, I mean, just show you a glimpse of also what we do in these areas. In particular, I mean, I would like to take a closer look very briefly at generalization, explainability, and then, I mean, we will delve a little bit deeper, and we will come in a very natural way to also the problem of sustainability. So, as said, generalization, I think this is one of the most important theoretical directions in mathematical foundations of AI. So I would like to just show you one, let's say, series of research, what we are pursuing. This is related to one particular type of neural network, which is these days also very popular. There are even conferences just dedicated to this, which are graph neural networks. So this is graph. This handles graph data. So graph signal is just a graph where each vector is associated with the Euclidean vector. And so here are a couple of examples: molecular design, so biology, networks, communication networks, recommender systems. And so the generalizations certainly ask, we have graph neural networks, we have some graphs in the training set, we have some in the test data set. Does graph neural networks generalize from our training data set to unseen graphs? That's the classical generalization question. here we can ask a sub-question which is not there for the Euclidean case. Here we can ask if the graphs are somehow alike, and this is this concept of transferability. If two graphs model the same phenomena, the question is how to make this precise, but let's bear with me for a moment. Then a trained neural network should have the same repercussion on both graphs. So it should handle both graphs in particular, almost the same way. The outcome should be not that much different. And what does it mean, the same phenomena? So you can view it as sampling from a metric space. There's also a graphone approach, where a graphone is a continuous object, a continuous graph in a certain sense, and you have graph sequences converging to this graphones, and if two graphs come from the same sequence, then you can label them as modeling the same phenomena. And so now the question is, I have maybe the graph on the right-hand side in my training data set and the graph on the left-hand side. I'm wondering what the repercussion then is. And I would like that this is close. And so what we did, this is one of the earliest results. I don't want to go much into the details. Here I just want to show you the thread of research. So we could bound the generalization error, so the transferability error of the graph Laplacian, and the consistency error, which is basically, in a certain sense, the density of the sampling if you view a graph as a sampling of a Euclidean space. And so many aspects were involved there. We first looked at the spectral situation where we had spectral filters. We developed a functionalistic framework. And then basically, the key idea of deriving this analysis was always to move via this overlaying continuous space from one graph to the other, and this way get the error bounds. So from that was basically the start, and then we have many results on generalization for graph, also convolutional neural network, for message passing graph neural networks, which are those, let's say, which are defined in the spatial domain as opposed to those in the spectral domain, which I alluded to before. So this is, there are no details here. You see, I just want to point towards, I think, very exciting directions where mathematics is extremely important, and which is also a very technical area. But these error bounds, this is what is these days missing. And for instance, in Germany, the German Telecommunication Agency is very hesitant to use AI right now because precisely these error bounds are missing. I would like to delve now a little bit more detail into explainability, because that's something also close, in a sense, close to my heart, because I think it deserves much more mathematics. So what is explainability? I'm sure you've seen pictures of this type. So you have a 3, you input it in your neural network, let's say. The network correctly classifies this as a 3. And then the question is, what did the network look at to decide that this is a 3? And the explainability approaches basically put a heat map on top of the input image, indicating where the network looked at. So here it looked at the red pixels, which are these openings, and that makes sense because that distinguishes a 3 from an 8. But then, if you look at the image on the right-hand side, so here the network correctly classified this as a horse. But now look at where the network looked at. So it looked just at this copyright tag.
Hello, Gitta. The slides are not changing.
Sorry?
The slides are not getting changed. Only the first one is fixed. So,
the slides
are you
not
moving
moving?
to the? No, the slides are not moving.
Oh, the slides are not moving. Oh, okay. That's actually a huge problem. I'm sorry. So, okay. Yeah, I don't know. With Google Meet, I usually don't work. So, okay. So how do I do that? Let's see. Let me try again. Oh. Okay. Are they moving now?
Yes. Now they're moving.
Okay, I see. So, okay, so should I start over or should I continue from where, you got the first part or?
और स्लाइड टा ये হয়নি বলে বলতে সাধারণ স্লাইডটা চেঞ্জ করে দিই
A quick revision from the.
Okay, so maybe I can just say very briefly, what I said.
না চেঞ্জ করেন
Yeah, so Yeah, so AI is basically infusing our lives, as you see here, in various manners, different parts of our critical infrastructure. Also on the bottom, you see that science is also very much impacted. Yeah? So in mathematics, we even have now Lean, which helps with proving and also verification of proofs. But in this whole range, if AI becomes part of critical infrastructure, reliability and sustainability are key aspects. So starting with reliability, I discussed what are key problems these days with reliability, like safety, security, responsibility. And I argued that, I mean, AI is a mathematical discipline, so all those terms, model, learning, representation, power, we can mirror in the mathematical world, functions, optimization, and so on. So in that sense, I mean, understanding AI requires mathematics. It cannot, I mean, it is mathematics in a certain sense, and so just to be on the same page, yeah, so it's the definition of a deep neural network. So then, I mean, the question is, what are now key directions people are interested in to ensure reliability from a mathematical perspective? And there are these three directions: expressivity, learning, generalization, which many people work in different areas. Expressivity typically being approximation theory, learning more optimization, and generalization is typically statistical learning theory. And the fourth is explainability, which is a bit different. There you want to understand an existing system, but nevertheless very important if you want to ensure reliability, trustworthiness. I mean, then I discussed a bit about generalization, just, I mean, on a very high level. So just now we discussed graph neural networks. So these are neural networks acting on graph signals. There are many applications in this direction, and just very briefly discussed, and also that was more on a high level. Right now, graph neural networks and one particular generalization aspect. So if you have graphs which are somehow alike, then you would like that if you apply a graph neural network, it has the same repercussion on both graphs. So it handles both graphs in the same way, and so this similarity between different graphs. There are various mathematical concepts you can apply, for instance, metric space sampling graph forms. And then, I mean, here the key message was, I mean, we derived one first result. This was one of the start in this direction to estimate the generalization error, for instance, by the transferability error of the graph Laplacian and consistency error. And so this was the start of many results in this direction. So this was just a very, let's say, very brief glimpse into generalization. And now let's start with explainability. So here, I mean, on the right-hand side, so this was, I think, the last, what we then discussed. So here you have a horse. The network says this is a horse, but the explainability approach just shows that the network just looks at the copyright tag. And so then you see something, a mistake happened during the training process. What happened was the training data was biased. So all images of horses had this copyright tag. And so the network did the next best, the easiest thing, what it could do, it could just learn the copyright. And so this you can find out via explainability. Now, the ultimate vision is to discuss with AI, like with a human, the reason for decisions. But I mean, from my viewpoint, what is absolutely crucial in this area and what is still to a certain extent missing is if you use explainability to ensure reliability, then the explainability approach itself has to be reliable because you have to trust the explanation. And that you can only do if you're on solid mathematical feet. So therefore, I mean, mathematics is needed to make the explanations reliable, defining what relevance, and so these are also called relevance maps. So what is an optimal explanation? Also, maybe not every pixel is important. And so let me show you one result which we derived, where we viewed explainability as a trade-off between information and distortion. It comes from information theory. So information theory in general is the following. So we have two persons. One has a message. He transfers parts of the message to Bob. Bob decodes it, and he will make an error. And so they have this trade-off between how much is sent and the error of decoding. And so now you can formulate this you can formulate explainability in this framework. Alice and Bob have the neural network. Alice has the original image, and she transmits part of the message to Bob, hopefully the relevant part. Then Bob brings that back to image size, maybe by obfuscating by random pixels, because this not distort the meaning too much, and when he puts it in the neural network. So you have the distortion, which is the difference, the expected value of the difference between phi of x and phi of y, and you have how much pixels are sent. And so you can formulate this in a optimization problem. So you have here d of s, that is the distortion, that's the expected value of phi of x minus phi of y. And then ideally here you would have, in this part, lambda times the number of pixels. But we all know that this optimization problem you cannot solve because it's combinatorial optimization problem. So instead we relax and we put now a relevance score on every pixel, and we replace the number of pixels by the little L1 norm. Then you can solve this problem, and you can make it a bit also more suitable by, for instance, using decompositions of the data like wavelet decompositions, and then put the relevance scores on the coefficients. So that means you don't put a relevance score on every pixels, but on natural clusters of pixels. So, in this way, if you drive such a mathematical approach, you can actually really also derive concrete theorems. And I would like to show you one. Before I do that, let me show you one application. So this is an application which comes from telecommunication. If you look on the left-hand side, you see the blue buildings, the blue objects, these are buildings. The red dots are cell phone users. And the white area in the middle, not the green one, the white area here in the middle is the cell tower. And now the network computed this black and white background, which is the so-called radio map, which indicated the strength of the signal. But then, if you look at this green area, what you see is there's an area of bad reception, although you are standing in front, directly in front of the cell tower. And so you can ask this area, this green area, how did the network come to that decision what to put in there? On the right-hand side, you see the explanation. So also the network looked at these cell phone users, these red dots, and in fact they have not that good reception. And what turned out later on was there was actually a building missing in the city map. So the data was faulty, the network did something correct. So that means explainability can also help us reveal these underlying structures. So now let me show you also one concrete result. So we notice the following problem with explainability approaches. If you look at the image on the left-hand side, it's a classical image called cloak, and you see here the edges in the image. And then we look at different explanations, shaded X and RDE, and each time at the edge structure. And what you notice is that the shaded X edge structure is a subset of the edge structure of the cloak, but with RDE, additional edges are invented. So in that sense, this explainability approach is not faithful, so it distorts the meaning. And this is something which we can rigorously prove. So if we model X as an L2 function, and we have our mask M, and so now we extend everything from wavelets to shearlets, which are more directional objects. Then if Y is the explanation and X the original image, the wavefront set of Y is always a subset of the wavefront set of X. And those who are not familiar with the term of a wavefront set, so the wavefront set are the singularities together with the direction. So that means, in layman's terms, the edge structure of Y is always a subset of the X structure of the original image. Yeah, and so this is what I mean by if you have a mathematical foundation, you can actually trust theory. So now we can ask, I mean, a bit provocatively, can reliability always be achieved? Can we just go for better models, better explanations, or is something more fundamental happening? And this brings me now to actually look at more fundamental issues, which is actually where we compute, which we use for our algorithms. And we notice that the current state of the art is digital hardware. So we break everything down to zeros and ones, and so the question is, does this cause any problems, maybe even some systematic error? And what we found out is, and there's actually, I mean, a beautiful theory, which is very close to mathematical logic, which is called computability theory. And so what we could show is that if you look at solutions of finite dimensional inverse problems, they are not Turing computable. And so that means the Turing machine is a model for a digital computer. And so those are not computable on digital hardware by a neural network. So that doesn't mean every algorithm is wrong. So what it means that these algorithms, which are more or less universal, that they could fail sometimes, and this is unavoidable, and we don't know when this happens. So there could be some systematic errors in the background. This is the hard to concrete result. So here we, for instance, looked at a very specific solver of an inverse problem AX is equal to Y. It's a sparse regularization with the one norm. And let's psi, the solution set, and then we could show we cannot find a Turing computable function psi hat, which approximates psi up to 1/4. And so this is far off machine precision. So this shows there's something fundamentally going on if we use digital hardware. And we have many results in this direction also for classification problems, optimization problems, even certain types of PDEs computing the pseudo inverse. And even you can transfer that to quantum algorithms, because for quantum algorithms, I mean, also you need to do certain computations beforehand on digital hardware. And so also those then have those problems. So this is actually, I mean, a bit concerning. I mean, I hope you agree. And so that means we currently mostly look at the top of the iceberg. We look at models like neural networks, transformers, and so on. We want to make our data as clean as possible. We look at the training procedure. But underneath the surface, there's something much more fundamental going on, the hardware, the computing paradigms. So the future of AI might not be only looking, let's say, at the tip of the iceberg, but we also need to dig deeper also as mathematicians. And so in the last minutes, I would like to show you a little bit, I mean, something, let's say, under the surface. Because, I mean, on the positive side, what we could show is that things become computable. So here, solution of a finite dimensional inverse problem. If we go to the analog world, and there's an analog of the Turing machine, which is the Bloom-Trup-Smale machine. And there are actually very interesting developments concerning analog machines these days. Like, for instance, neuromorphic computing, biocomputing, where people use stem cells for computing, quantum computing. And interestingly enough, I mean, neuromorphic computing is also considered much more energy efficient. And so this brings me also now in a very natural way to sustainability. So the question is, can we get reliability and maybe also sustainability at the same time by also reconsidering the way we do computing? And so the very last minutes, I would like to now use in particular also on sustainability. Sustainability is a major problem. It's more severe than it's currently openly discussed. So what you see, for instance, in the US, I mean, there are new hyperscalers and immediately new nuclear power plants need to be built just to provide the amount of energy which they already need these days. And if you look at the image on the right-hand side, you see here the world energy production. And the curves you see, this is the energy just for communication. And you might know that in a computer, these days, most of the energy actually goes to communication and not to the actually, computing image. But what you notice here on the lines is you can lower this curve and you can lower the point when this crosses the world energy production, which should be a major problem, if you change the hardware, if you go from CPUs to GPUs, maybe to novel platforms, and then if you use also on the software side novel methods, and here so that's this post-Fanon approach in communication. Not going into the details, but the key message here is, first of all, the energy crisis, the sustainability crisis is much more severe than it's currently discussed and will hit us in the future. And secondly, it is not enough to just look at the software side and the algorithm side. We also need to combine it with reconsidering the way we do compute. And so why is neuromorphic computing so exciting? If we now for a moment compare a high-performance GPU with the human brain, what we immediately notice is the difference in energy consumption for a particular task, and also obviously the type of computing. Our brain is analog, adaptive, biological. And so this coincides with the way we do computing these days for Neumann architecture with a binary input and binary output, as opposed to the human brain, and neuromorphic architectures go in that way. They have a spike train as an input and a spike train as an output. And on the chip, there's basically like a neural network to a certain extent. So, and there are also many results, let's say empirical results, which show this energy efficiency, and maybe not going too much into details here. So what you see here on the right-hand side is, for this multidimensional harmonic retrieval algorithms, also a GPU needs an enormous amount of energy versus the green is always the neuromorphic part where this is. And also, if you look at the accuracy, even there, the neuromorphic approach is much more energy efficient. And I would like to show you now in the last minutes that you can also do hard mathematics in that respect. So first of all, let me just show you, the, let's say the intuition. The neural networks you run on this neuromorphic hardware are further developed as opposed to the normal neural networks where you compute layer by layer. So here, each neuron acts on its own. So you get your spike trains as input, and then if you look at this neuron N3, so this neuron N3 has a potential. You see that on the right-hand side. And each time a new, let's say, input comes from another neuron, it's slowly building up its potential. And at some point, the threshold will be reached, and then it will fire. That means every neuron acts individually, and time is a crucial component. And so you can store also information in time, and that doesn't cost additional money. So that's one of the reasons why it's more energy efficient. And so here, in all its glory is the mathematical definition. And let me say, this is the easiest definition of a spiking neural network. This goes up to stochastic PDEs, because you can imagine, for, let's say, even one neuron in the human brain, it's extremely difficult to model it. But so here, this is the easiest model. That's a spike response model. And maybe let's briefly go through that. So it's a directed graph. Again, you have a subset of inputs. You have a subset of connections, or you have connections. And now every connection, every edge has a weight that is like a normal neural network. So there we also have weights. But then it has a delay, and it has a response function. And now every neuron has a threshold that's like the bias before, but then it has this membrane potential, and here you see the formula for it, which building up over time, it gets each time these inputs from connecting neurons at their firing times, and then at some point it reaches the threshold and then it fires. And so what we did, one of our first results was in expressivity. Expressivity you can view in two different ways. You can look at it from a functional viewpoint, from an approximation viewpoint. and ask, I have certain function classes, to which extent can I approximate them efficiently? The second is I look at the input space and look at how many linear regions it is tiled into, and that also gives me another measure of expressivity. And so let me first show you the high-level view, and then on the next slide you will see the mathematical formulas, but so that it's easy to get the intuition. So what we did was, one aspect what we did was we simulated a normal neural network by a spiking neural network, and vice versa, it's more expressive. When we simulate a classical neural network by a spiking neural network, we need only a linear scaling of the number of neurons and the depths. On the opposite side, often requires an exponential scaling if we simulate a spiking network by a normal neural network. Yeah, so that shows this one aspect that spiking networks are more expressive. Now this is how it looks in detail. So here in the first part, you have your classical ReLU neural network of a certain depth and width. And so then we constructed a spiking network, and you see here the number of neurons and the depths, and that depends all only linearly on capital L. And if you do it the other way around, you have even a one-layer spiking network, and you want to realize this by a ReLU neural network, you see you get these exponential terms. I should fairly say this is not a lower bound. For some cases we could prove that this is a lower bound, but so let's say showing that it's a lower bound for this whole result is still missing. And so there are many directions you can go in the future, and more people jump into this area now of, let's say, sustainable AI spiking networks. You can look at training algorithm generalization. You can ask very similar questions to before, but you can also ask additional questions, because these these networks are in particular good for sequential data, like also our human brain. And so you can ask questions about how it handles this, about stability. Also, we are now working on making, let's say, the energy consumption more rigorous, the analysis of it. Can you combine it with normal neural networks? I think it's a very exciting field. There are not too many people working in there, but you see with these big conferences, there are more and more people jumping on the wagon. And so, I mean, I think what we now saw is we started with reliability, and we saw that it's certainly connected to mathematical foundations, but also to the computing paradigms via computability. But then we saw that sustainability also has these two connections. So we can drive mathematical foundations by now looking, for instance, at spiking networks, and it's even intrinsically linked also to computing paradigms. Yeah, so mathematical foundation computing paradigms, I mean, this is basically, I mean, the link between reliability and sustainability in both areas needed. Now, I mean, in Germany, I mean, between two states, we are also driving a major initiative, next generation AI computing, where we aim for a theory, for a mathematical driven framework for the next generation of AI systems, I say of green AI systems, with applications in communication, medicine, and robotics. And so let me just finally say one aspect, what is, I think, will be also important for the future. And so I showed you that it's not sufficient to only look at the AI models. One also need to take into account where we compute on. So we have many approaches, quantization, compression, and so on, to make everything more efficient. But then if we neglect the hardware part, this will be very difficult or impossible, basically, to then make into really viable AI systems. In that sense, you can say we must move from these model-centric or algorithmic-centric AI to system-centric AI, where we look also from mathematical viewpoint at the whole AI system. So let me conclude. We talked about this challenge of reliable and sustainable AI. We started with from the viewpoint of reliability. We saw that mathematics has, I mean, can contribute significantly to that area. In fact, I mean, I said AI is a mathematical discipline, looking at expressivity, training, generalization, explainability. But then we saw that if we dig deeper on the reliability side, there are fundamental problems with the current digital hardware. And so that brought us to novel hardware paradigms like analog systems, which at the same time are also more sustainable. So therefore, I mean, just to conclude, from my viewpoint, if we aim for reliable, sustainable AI, that requires a mathematically grounded model hardware co-design, in any case, a very substantial mathematical foundation. And with this, I'd like to conclude and thank you very much for your attention.
Thank you, Professor Gitta Kutyniok, for your wonderful lecture and inspiring lecture, which will be motivating definitely us to work on this area of mathematics or AI. So, one, two quick questions from the audience, if there is any. Okay, if there is a question, I'll ask. Some people are apprehending things that we are going sustainable in that area. So, those any kind like topic or one has AI, we can generate a new AI by themselves.
I'm sorry, the internet connection is quite...
low and that be a straight human kind of.
I'm sorry, the internet connection seems to be very bad right now, so can you hear me or?
So can you hear me?
Now I can hear you better, yes. Can you, sorry, I couldn't understand your question.
Okay, I was asking that the AI are now growing more reliable and sustainable, and you are also working on that area. So people are apprehending that is there any possibility in future that AI will become a threat to humankind, so that the AI will generate some new AI, new model by themselves, and will be out of control of humankind? Is there any possibility?
I mean, that's an interesting question. I think people are worried about that. I wouldn't exclude that possibility, yeah, but I think it's a task of. I think the more danger is that people abuse AI for their purposes. I think that's the most danger, not that much that AI takes over in some sense. But I think what is key now is that, I mean, there are sufficient, let's say, control mechanisms also worldwide as a world community concerning AI, and many people are working towards that. I mean, there's also now the United Nations who set up a large-scale committee. So in that sense, I think this will be a task for us these next years, because so the development is extremely quick, which is also one major problem. But I think from the mathematical side, we have also the chance to contribute.
So thank you very much for delivering this lecture despite of your extremely busy schedule. We are very much grateful to you. And as a gesture of token, we would like to confer you a certificate of Research Excellence Award. If you please accept, I'll display that. Okay.
Thank you so very much.
So please. Is it visible to everyone? The certificate? Can someone confirm?
No.
No.
I cannot see. No.
Let me try 1 second. I think it's visible now.
Yes.
Okay, so let me read it out. This Research Excellence Award is being presented to Professor Gitta Kutyniok Bavarian AI Chair of Ludwig Maximilians University at München in recognition of our significant contributions in the areas of mathematical foundation of deep learning, applied and computational harmonic analysis, explainable AI and reliability, and AI for mathematics. Her contribution has led to significant advances in applied mathematics and AI research and has provided tangible benefits in solving complex real-world problems. So we are uh, happy to provide you this certificate. Please accept it, and
Thank you so much.
I'll be sending this certificate to you over mail.
Thank you so very much. I mean, that's a great honor for me. So I'm very grateful to you. This is, yeah, a wonderful surprise, and I'm very, very happy about it. Thank you so much.
Okay. Thank you. Thank you very much. So with this, we conclude the very first